Hello and welcome to Chemistry Masters. In this video, we are going to bring the concept of filling of pi molecular orbital of various systems which we have discussed in our earlier lecture, like ethene, molecular orbital of 1,3-butadiene, as well as we will be discussing the electron filling in the case of allyl system like allyl cation, allyl anion and allyl radicals. Apart from this, in this video, we will also go through the concept of HOMO and LUMO, which are one of the most important concepts which should be known to us when we are discussing the pericyclic reaction. So hope this video will be giving you an idea that how these electrons are filled and what is the particular concept of HOMO and LUMO and how these HOMO and LUMO can be decided in various type of conditions which are being followed in pericyclic reaction. So let us begin. So in the previous lectures we already have discussed about the formation of pi molecular orbital of various systems. So here let us take the example of electron filling in the case of ethene pi molecular orbital, that how in thermal condition as well as in HNU condition, that is in photo condition or light condition, how does the electron are filled, and then we will be discussing about the concept of HOMO and LUMO. So if you remember the earlier video, in that we already have discussed that in ethene there is formation of two pi molecular orbitals. One is designated as psi1 while another one is designated as psi2 star. It only tells that the lower one is bonding molecular orbital, the above one is anti-bonding molecular orbital, and the anti-bonding molecular orbital are always equal to the number of bonding molecular orbital. And the star here tells you that this is an anti-bonding molecular orbital. Now we will discuss that how the electrons are filled in these pi molecular orbital of ethene. So if you talk about the condition, so we already have discussed that the pericyclic reaction can happen in two conditions. The first one is thermal condition and the second one is HNU condition. Thermal condition is also shown as this triangle structure, which actually tells you that the reaction is happening in condition of heat. Now we will see that how does the electron are filled. So before understanding that how does these electrons are filled, we should be knowing that how many electron will be there in this pi molecular orbital of ethene. So if you talk about ethene, ethene is CH2 double bond CH2, means there are 2 pi electrons. So what we have to do, we have to fill 2 pi electrons in these two molecular orbitals which has been shown here. One is your psi1, another one is your psi2, and we are filling it in condition of heat out here. Now when you are filling the electrons, so we should be knowing about Hund's rule of electron filling as well as the Pauli's exclusion law. These are very much important, which you have studied in your lower classes. So whenever you are filling the electrons, the first concept is that the electrons are always filled in lower energy level first. Means 2 pi electrons which we are having here in this ethene molecule, these electrons will be started to fill from the lower energy level. The first electron will go here. Now if you talk about another law, the another law says that until one of the orbital is filled, the electron can't go to the next energy level or next orbital. So what will happen, as you will see that the bonding molecular orbital and the anti-bonding molecular orbital, they are having different energy. That's why here what will happen, the second electron will also get filled in this psi1 orbital, or you can say bonding molecular orbital. because it is of lower energy as compared to anti-bonding molecular orbital. And whenever you talk about the filling of electron, we all know that in a particular orbital, the 2 electrons which are filled there will be presence of maximum 2 electrons, and the 2 electrons which are filled there, they are having opposite spin, plus half and minus half. So this is how the electrons or the 2 pi electrons will be filled in pi molecular orbital of ethene, and where we have seen that the both of the electrons will go to the psi1, that is bonding molecular orbital. Now the same 2 electrons, how they will be filled in HNU condition or in light condition, we will be discussing that. So if you talk about a light conditions, so again there will be 2 orbitals. One will be again your psi1, another one will be psi2 star, which will be designating the bonding molecular orbital and anti-bonding molecular orbital respectively. Whenever we are providing the light to the system or to the pi molecular orbital system, in that case what happened, there is excitation of electron. It will generate the excitation of one of the electron from the lower energy level to the high energy level. So in the normal condition what happened, both of the electrons are filled like that. But in HNU condition what will happen, one of the electron will get excited and it will go to the high energy level like this. So one of the electron will get filled in the psi1, that is bonding molecular orbital. The another electron will get excited to the psi2 star, that is your anti-bonding molecular orbital. So this is how the 2 pi electrons of ethene will get accommodate in the pi molecular orbitals, as here we have shown that. So hope you have understand the concept that how the electrons will be filled in thermal condition and HNU condition. Now a very much important concept lies here, that is known as HOMO and LUMO. HOMO is highest occupied molecular orbital. The full form of HOMO is this. While if you talk about the another one, that is LUMO, that is lowest unoccupied molecular orbital. These two particular concepts are very much important in case of pericyclic reaction. So HOMO, as the name suggests, highest occupied molecular orbital. It is that orbital which is having electron and it is of highest energy among all those molecular orbital which are having electrons in them. So we can take the example out here. So if you talk about a thermal condition, in thermal condition you can see that there is only one orbital which is having electron in it, while the psi2 star orbital doesn't have any electron in it. That's why this molecular orbital can be considered as HOMO. So here you can say that in case of thermal condition, the psi1 orbital, or you can say your bonding molecular orbital, is HOMO. However, if you talk about this orbital is considered to be as the LUMO, that is lowest unoccupied molecular orbital. That means that molecular orbital which doesn't have any electron in it and it is present at the lowest energy level out of all those molecular orbital which doesn't contain any electron in them. That picture of HOMO and LUMO would be very clear in coming examples also. So in this case, in thermal condition, psi1 will be the HOMO and psi2 star will be LUMO. Now if you talk about the HNU condition, so if you talk about HNU condition, you can see that the psi1 is also having electron, one electron is out there, and psi2 star, that is your anti-bonding molecular orbital, also contain electron. So this molecular orbital is also occupied molecular orbital. Psi2 star is also an occupied molecular orbital, but out of these two, this one is at the higher energy, that is your psi2. That's why in HNU condition, psi2 star would be termed as HOMO, while in case of HNU condition in ethene, there will be no LUMO, means there is no orbital where there is no electron. So no unoccupied orbital is there. That's why the concept of LUMO in case of HNU condition in ethene molecule doesn't exist. This HOMO and LUMO are also known as FMO, that is frontier molecular orbital. So hope a picture of HOMO and LUMO would have been clear in your mind. Let us clear this case of HOMO and LUMO with another example, that is of 1,3 butadiene. So if you talk about 1,3 butadiene, we already have discussed in our previous video, whose link is present in the description also. There are 4 molecular orbital in that. So before that, we should be knowing about the structure of 1,3 butadiene. It is somewhat like this. So you can see that there are 2 pi bonds, or you can say there is presence of 4 atomic orbitals. These 4 atomic orbitals overlap with each other to give you 4 molecular orbital, which can be designated as psi1, psi2, psi3 and psi4, out of which psi3 and psi4 are written as psi3 star and psi4 star because these two are anti-bonding molecular orbitals, while psi1 and psi2 are your bonding molecular orbital. And we all know that the bonding molecular orbital are always in equal number to anti-bonding molecular orbital. Now again here we will be first understanding that how does the electron are filled in thermal condition. Then we will go with the photo conditions, that is light condition, and then we will discuss about the HOMO and LUMO in case of 1,3 butadiene molecule. So if you talk about the 4 orbitals, that is psi1, psi2, psi3 star and psi4, the electron will be filled in these 4 molecular orbital. Now before that, we should be knowing that how many electrons are present in the case of 1,3 butadiene. So in case of 1,3 butadiene, there are 2 pi bonds which correspond to overall 4 pi electrons. Now these 4 pi electrons will be filled according to Hund's and Pauli's rule, which we already have discussed in the case of ethene also, that the electrons will be started to fill from the lower energy level. Once the lower energy level is completely filled, then the electron will be going to the higher energy level, and a single orbital will be containing maximum of 2 electrons. Now let us see that how in thermal condition the electron will be filled. So in thermal condition, at first out of these 4 electrons, the first and second will be filled like this. Once this molecular orbital, that is psi1, is completely filled, then the next 2 electron will go to the next higher level. So this is how the 4 electron will be filled in case of 1,3 butadiene. Let us talk about the HOMO and LUMO in this case. So out of these two, if you see, the psi1 and psi2 both are filled with the electron, while psi3 star and psi4 star are not having any electron in them. That's why you can say that these 2 orbitals are occupied molecular orbitals, while these 2 are unoccupied molecular orbital. Now if you talk about the condition of HOMO and LUMO, so HOMO is highest occupied molecular orbital, that occupied molecular orbital which is at highest energy. So out of the 4 molecular orbital which are present here, the psi1 and psi2 are the occupied molecular orbital, and out of them this psi2 is the occupied molecular orbital which is present as the higher energy, and that's why you will be calling this psi2 as the HOMO in this condition. While if you talk about the next 2, these both, that is psi3 star and psi4 star, are unoccupied molecular orbital. Out of them, the lower one is this. This is your lowest unoccupied molecular orbital. So here the picture is more clear as compared to ethene molecule, that orbital which is having electron lastly filled in it, that will be your HOMO, and next to that the orbital which is present there, that will be considered as LUMO. Those are psi 2 and psi 3 star respectively in the case of thermally conducted reaction of pericyclic reaction. Now if you talk about HNU conditions, now in HNU conditions again there will be electrons, and these 4 pi electrons will be filled here also. Now let us see that how these 4 pi electrons are filled. So normally the 4 electrons are filled like this when we are talking about the thermal condition. But as soon as you talk about the irradiation of the molecule with the help of light, one of the electron will get excited. Now there are 4 electrons, and if you talk about the excitation, certainly what will happen, the electron will get excited to the next energy level. And here we have to understand that which electron will get excited. So if you talk about the electron present at psi 1, they will not get excited from here, because the energy gap between this psi 1, that is this orbital, and psi 3 orbital where it get excited, it is too large. That's why what will happen, the electron which are present in psi 2 orbital or psi 2 molecular orbital, one of them will get excited to the psi 3 star orbital. So you can show it like this. So the electron from this psi 2 molecular orbital will get excited to psi 3 star molecular orbital. So this is how the excitation will take place. Now we will discuss about the HOMO and LUMO condition. So if you talk about the HOMO and LUMO out here, so this psi 3 star, you can see that this is the last orbital, or this is the highest orbital where the electron is filled. So this occupied molecular orbital will be called as HOMO out here, while there is only one orbital or one molecular orbital which doesn't contain any electron in it. That's why it is only unoccupied molecular orbital, as well as it is the lowest unoccupied molecular orbital out here in case of HNU condition, where 1,3-butadiene is taken as the example. Now we will see the third type of system in our example, that is allyl system. In case of allyl, we already have discussed that there will be presence of 3 molecular orbital. For that you can see our previous videos. The link about that is given in the description also. That will tell that why 3 molecular orbitals are formed there and how they are formed. Whenever these 3 orbitals are formed, they will be designated as psi 1, psi 2 and psi 3 star. Out of them, the lowest one is called as the bonding molecular orbital. The highest one is your anti-bonding molecular orbital, while the middle one is known as non-bonding orbital. The 3 orbitals are present here, and corresponding to 3 molecular orbitals we have to fill the electron. Now if you talk about these allyl system, we are having 3 type of allyl system. One is your allyl cation, which can be shown as this. One is allyl anion, which can be shown as this. And third one is allyl radical, which can be shown as in this way. We will see here that how in thermal condition and HNU condition the electrons are filled in allyl cation, allyl anion and allyl radical, as well as what will be the condition of HOMO and LUMO in case of all these allyl system. So let us take the example of for all of them one by one. So firstly we will be going with allyl cations. So if you talk about allyl cations, we have to see here that how many electrons are there which are undergoing in pericyclic reaction. Now if you talk about
this particular condition, there is only a single pi bond, or there are 2 pi electron in this system only. That means overall you can say there are only 2 electrons which are undergoing the reaction. Now in this case what will happen, as we are having only 2 electrons, that's why what will happen, the electron will be filled according to the rule which we have discussed earlier, and both of the electron will be filled like this. And this will be HOMO in this case. So you can say in case of allyl cation, psi1 will be the HOMO, while next to that will be LUMO. Now if you talk about allyl anion system, in this also we are having 3 molecular orbital where the electron will be filled. Now in this case we have to first decide that, or we have to understand that how many pi electrons or how many electrons are there which are undergoing the pericyclic reaction. So again we are having a pi bond, that means there are 2 pi electrons, as well as you can see that there is a negative charge. Negative charge is associated with 2 electrons. So overall you can say that we are having 4 electrons which are associated with the pericyclic reaction in case of allyl anion. So these 4 electrons will be filled in this way in thermal condition. So in this case this side 2 will be our HOMO, because this is the orbital which is occupied, as well as it is in the higher energy as compared to psi1, and the next energy level, your psi3 star, will be considered as LUMO. Now if you talk about the third case, that is allyl radical. In allyl radical we have to see that how many electrons are present here. So again there is a pi bond, means 2 pi electrons are there, and a radical is there, that means 1 electron. So overall you can see that there are 3 electrons in this system. So these 3 electrons can be filled in this way. The first 2 electrons will go in the lowest energy level, the next electron will go in the high energy level. So this will be our HOMO. So psi2 will be our HOMO, while psi3 star will be our LUMO in case of thermal condition here for allyl radicals. Now the same condition we will see that if we are irradiating all these molecules with the light, how does the condition of electron filling get changed, and respectively how does the HOMO and LUMO for the molecule get changed. The first, again we are taking the example of allyl cation. So here what will happen, the molecule will get irradiated, the electron will get energy and it will get excited, and one of the electron will jump to the next level. As soon as the electron goes to the next level, this will become our HOMO, that is your psi2 will become HOMO, and psi3 star will become LUMO in this case. If you talk about the HNU condition for allyl anion, in that case the lower electrons, those which are present in psi1, they will remain there, but one of the electron from the psi2 or molecular orbital will get excited and it will reach to the next energy level, that is psi3 star, that is anti-bonding molecular orbital, and the HOMO will get changed. So psi3 star will become HOMO and there will be no LUMO in this case. And when you talk about the third condition, or that is of allyl radical, here in this case with the irradiation with the help of light, the electron will get excited to the next energy level. Excited state of allyl radical is not easily available over the various readings. You will find very less video as well as very less readings in which you will see that the excited state of allyl radical has been shown. So actually I have found one of the source from where I am telling you that how does the excitation of electrons in the case of light condition in allyl radical happens. The link about that has been given in the description also. You can check it from there. So in this case, generally what happened, the electron, as you can see in thermal condition, two of the electrons are present in psi1 orbital, while one of the electron is present in psi2 orbital. When we are providing the energy in form of light to the allyl radical system, the electron which is present at this HOMO, it get excited to this psi3 star level, leaving a condition of vacant molecular orbital at psi2. Now what happened? This electron which is present at the lower level, that is psi1 level, it also get excited to the next energy level, that is psi2. Give you such a condition. And here again the HOMO becomes your psi3 star, which doesn't leave any condition of LUMO. So this is how the condition of electron filling in thermal condition as well as in photochemical conditions will be there in case of all the pi systems which we have discussed here. As well as we hope that you have understand the concept of HOMO and LUMO, which are one of the major concepts which will be used in all the coming reactions also, mainly in case of electrocyclic reaction and cycloaddition reaction. So we will be bringing other concept in our coming videos also. So hope that you will be continuing with us in the same way. Share our video with your friends and subscribe our channel for more. Thank you.